Good morning, everybody. I love the energy I feel in this room today. Is there something like good going on in the world? Or?
Well, A, it's Friday, and B, there's a giant joke on the board.
Yeah. Today we will be talking about combustion analysis. Or are you talking about solutions? Yes? Okay. Did you see my comment?
Yes, but I thought I did that whenever I worked it out.
Yeah, so yours was something slightly different, and so I'll try to touch on it today. We're not going to spend a lot of time on molarity today. I'm going to give you enough so you can start to do some of the stuff on your own. So if I don't answer a specific question, remind me and I'll try to address that, all right? All right. As Jackson said, we have our first joke of the semester on the board. So what is our definition of a solution? Which one of these two do you guys feel best about? We have a mix between the two correct answers.
I'm going to go with D because I just wanted to make it laugh. Yes, it is the answer to a problem.
As well as
a solvent that has a solute, or that contains a solute dissolved in it.
So a lot of people think about solutions as a drink, right? Your drink is a solution. It has the solvent. What is the solvent in most of our drinks?
Water.
Most of the stuff that we deal with outside of a chemistry lab, our solvent's going to be water. It's the thing that is typically in excess, and it usually, not always, dissolves the solute. And then the solute is the thing that's dissolved within it that has less parts. It does not always have to be a liquid.
It could be a gas.
If you move your hands around, you're moving your hands through a solution
Of air.
So a solution of air. Does anyone know what the solvent is? We're talking about air. What's the major component?
Nitrogen.
Nitrogen gas, N2 gas. 78% of the air molecules are nitrogen gas. About 20 to 21% of them are oxygen gas, so that's a solute. And then we have carbon dioxide and a few other gases as well. So that term, really, I want you to start thinking about it as looking at a whole bunch of molecules that are all mixed together evenly. Which one is there in excess, and which one is the one that's in lesser amounts. So this is typically what you think of, right? We take some sort of compound, we dissolve it into a huge molar excess, a lot more moles of water than there is of the solute, and then when they're together, it has to be a homogeneous solution. It has to be an even mixture everywhere. If it's not even, then there's different ways we talk about those solutions.
That looks like copper sulfate.
It might be. So we want to think about the solvent and the solute in a lot of different ways. So one of them I just mentioned is our drinks, right? So in this drink, the solvent is still water, even though there's a ton of things in it. This is a latte, which means that there's milk, but milk is composed mostly of water. And then we have sucrose, we have sugar in there. We have caffeine. We have a whole bunch of other things within that. So if we're thinking about water quality, there's some things in water that are beneficial that we choose to put in water, and there's other things that are not beneficial. And I want us thinking about what that ratio is, what the relationship is between the things that are in our water. Do you guys know where that's from?
Oh, God.
Yep. So that's Flint, Michigan. So that's drinking water that's coming out of the taps. Still is coming out of the taps in a lot of neighborhoods. Yeah. What are some of the things in that water that maybe aren't so ideal? So iron is potentially decent. Lead is the thing that's really becoming an issue. And a lot of lead pipes are fine. But we'll be talking about second semester solubility rules. We can have lead pipes and none of that dissolves in the water until we add nitrates to it. And we can get lead nitrate, which is soluble. You guys know that from your solubility rules. And so certain ions will pull lead into solution, which means we drink it and you can end up with lead toxicity. There was another set of issues we saw in the news the last few years. Did anyone see the news about Lake Erie? It's probably about 3 years ago now. And they weren't able to drink their water there because they had algae blooms that grew, and algae released microcystin LR, which is a small amino acid that actually forms a circle, and that's a toxic compound. So if you drink that, you have severe toxicity issues.
Very toxic compound, and they'll kill you in about 20 minutes, if I remember correctly.
If you drink enough of it. All right, so I want you to talk to your neighbors. How do we discuss what the amount of these positive or negative compounds are, not charges, right, in beneficial or deleterious compounds are in water? What are ways we describe how much is in water?
Like the term for it, though. Yeah, I know. I'm literally. No, I know what you're saying. I know.
All right, so I'm going to get some hand raised, some volunteers. How do we describe how much of those compounds exist in water? Kayla, give me one.
Can we do percent composition?
Percent composition, what do you mean by that?
How many moles of one thing is in comparison to the moles of the whole thing?
Okay, great. So we say how many moles of the toxin are dissolved in how many total moles of the solution. That's called mole fraction. We actually do it as a fraction instead of as a percentage. Absolutely. What are some other ways we can describe the amount of a solute in the solution? Sam?
Like parts per million or something like that.
Absolutely. So same idea, right? We have 1 million parts of our solution. How many are the solute? So we do this for gases. We talked about CO2 concentration in the air. Concentration went from 300 parts per million before the Industrial Revolution. Now we're well over 400 parts per million. Great. What are some other ways we describe that relationship? Jackson, one?
Yes. You could take the number of moles of of the solute in question, and take the volume of the solvent and of the solution in general.
Fantastic. So if we're talking about how many of them there are, the solute, in the total volume of the solution, what do we call that? So that's molarity. That's what you guys are working on in your homework. What's another way? Has anyone worked at a bar, ever been to a bar? What's a way? Not without her? Or you're volunteering her, you think she's been. So what are the ways in which, if you go to a bar and you buy an alcoholic beverage, what are the ways in which the amount of alcohol is described? Say again? I heard someone in this area say it. Trey?
By volume.
Okay, so what does that mean? What by volume?
Alcohol by volume in that instance.
Okay.
Come up with proof.
So proof is another way. I don't actually. I do know how it's calculated. It's really weird. So let's come back to that 1 second. What is the actual way that alcohol is described more technically?
Percent per volume.
So 12% of the volume is ethanol in wine, and that means that 88% of the volume is
Other stuff.
water, right? So it's a percent of the total volume comes from one solute, and the rest is from the solution. If we go to proof is it's double the percentage, right? Because if we have a solution that's 50% water and 50% ethanol by volume, you can light it on fire. And so what they said is, well, if we double that percentage, then we end up with 100 becomes the flammable point. So really, you could say the same thing, like 50% alcohol of any drink means you can light it on fire. So proof is a similar terminology to that. All right, so what I want us thinking about when we're talking about concentration, I don't want us thinking about, it's just another set of calculations. I want us actually picturing the mixture and saying that if we have different ratios of those things, we want to be able to describe the solute in a number of different ways. So let's do that next part. What are ways that we describe the quantity of a solute? Go ahead and write down in question number 2, I think it is. What are the ways we can describe how much solute there is? Write down all the units you can think of. And then do the same thing for the solvent. So just to clarify, looking at a couple people's paper, we're saying how do we describe the quantity of that solute? Not the ratio, we're not talking about the ratio yet, just the quantity. So can I get one volunteer to get us on the right track? Mohammed? Go ahead.
You can multiply the concentration of the
No, not multiplication, not all those things. Just what is one unit to describe how much of something we have? Josh? Ounces. Great, so volume. Ounces is one. Alright? Those are the kinds of things I want you guys to write down. Think about all the other ways we can describe how much of a solute we have. Quantity. Alright, so keep going, keep writing down how we describe the quantity. The amount.
But I don't like to think about
Alright, so can I have, we'll go around the room, we'll popcorn this out, so I want to hear from a number of different people. What are ways we can describe the amount of solute? I get different voices. Joey?
We did tons on the aircraft carrier.
Okay.
So much, so.
Fantastic. You have a lot of it. You're going to describe it in how many tons of solute you have. Kevin? Quart. Another volume of measurement of volume. Grams. Great. What else? How else can we describe how much? Love? Moles. Moles. How many of them we have, right? Are there other ones that you guys have?
Milliliters.
Milliliters. Great. We can do milliliters, liters, microliters. We can do all kinds of different volumes that revolve around the metric scale with liters. Any others that we missed that you want to share? Yeah, we could do the number of them in molecules as well as in moles.
parts per million.
Okay, so that's going back to a ratio. So yes, we can, and that relates to the number either in moles or the number in molecules, but compared to the solvent. Okay, so I want us thinking about, we can describe in a ton of different ways. Specifically, mass would be grams or tons or pounds or whatever it is. How many of them we have in molecules or moles. What the volume is, we can use tons of different measurements for that. All right, that describes how much solute we have. What about the quantity of solvent? Go ahead and write down some ideas if you haven't already. How can we describe how much solvent we have in a solution? Remember, not the ratio, just how much of it there is, what the quantity is. Take about 30 seconds to just try to force them out of your head, write them down. All right, let's go ahead and popcorn out. Can I hear from different voices? What are some ways to describe the quantity of the solvent?
Liters.
Liters, volume, right?
Grams.
Grams. Moles. Love is the mole guy today. Quarts. Any unit that we use to describe the solute can also be used to describe how much solvent we have. And so when we start talking about in chemistry, we're going to talk very specifically about the relative amount of the two of them, which is what a couple of us have been getting at. Right? Parts per million is one way to describe that. Molarity is one way to describe that. I want you getting out of the mentality of like, how do I multiply with this concentration? And start thinking about what is the ratio of solute to the solution or solute to the solvent. Some of our different forms of concentration use solution as the comparator. Some of them you compare the solute to the solvent specifically. So you will find units that tell you concentration with this ratio, and it can be any one of the top versions of the solute, right? We can say how heavy it is, how much volume it takes up, or how many of them there are. And then the solution, it could be any of those as well. And there's different names for all these different types of concentration, but really it's the exact same solution you're describing with different units. There's a few that just describe the ratio between the solute and only the solvent. Remember, the solvent does not include, it's not the total solution. Solution includes solute and solvent. So molality is one that you will find that uses this ratio on the right. You guys see the difference between these two?
I don't like how close the spelling are.
I think you're speaking for everyone in this class, right? So the names are incredibly close. The way we write the unit molarity is a capital M is molarity, and a lowercase m is molality. So if you ever see 1.2 little m, that's the one on the right. 1.2 big M, it's the one on the left. They're close, especially if you have a very dilute solution. If there's not much solute, then the liters is not going to be very different. But never assume that they're the same. All right, we're not going to spend a lot of time this semester, I think, on molality, but I wanted us to kind of get in the brain space to think about, we're describing this ratio, and we can do it any way we want. We just have to learn the molarity is that ratio. So if we look at this ratio, what's the first thing we should be thinking of? How might we use this ratio?
Finding moles per liter.
Okay, finding moles per liter, but
I think you're one a conversion factor,
yes.
but I have a question. So do we need to memorize that for the test? The one to the right for this test?
No, you're not going to be using this for the upcoming exam. We will be using molarity, so you need to know that when you see a capital M, you need to decompress that and write that that is, if it's 1.2 big M, it means 1.2 moles of solute in every 1 liter of solution. So once again, I want you making a sentence out of that relationship. If we have 1 liter, you know how many moles we have. If you have 2 liters, you know how many moles we have. If you have 0.5 liters, we know how many moles we have. So looking at these two different solutions, that's what I want you thinking of when you see a different concentration. So one of them has a different ratio of solute to the entire solution. One big disservice that Gen Chem books do to new students is they say, there's so much water here, we're not even going to show the water. Kind of messes with your head though, right? Because you're like, oh, it's a whole bunch of dots in an empty box. But in these types of examples, what they're saying is there is usually 1 billion times more water molecules than there are the solute. So if we showed all the water, you wouldn't be able to see the solute. We'll be working with examples of that kind of as we move forward. So, what do you call a tooth in a glass of water? 2 jokes today. All right. Let's go ahead and do a calculation with this. I want you to think about how we use this as a conversion factor. You're going to be using molarity in the lab next week. Or for the next week's lab, I should say. Some people are still doing the previous. And remember, you might just be able to do this calculation in your head, but please for now write out how you use molarity as a conversion factor. Raise your hand if you'd like a nudge for conversion. All right, let's bring it back together. So while I have trained you as a class a decent amount on how to use conversion factors, sometimes when you get a whole new set of conversion factors, it becomes uncomfortable. So if we're doing this, thinking about conversions, unit conversions, what do we always put on the far left side? What we start with, which in this case is the quantity of moles. Because 1.25 m, whenever you see 1.25 m, the first thing I want you to do is write 1.25 and then unpack the big M. Moles of solute, what's our solute in this case? Per 1 liter of HCl solution. Okay, so when you go to the chemistry stockroom, you can get a bottle of concentrated HCl that's 12 molar. You put your hand in that for a little while and it'll burn all your skin off. So we dilute it and make weaker solutions that you use in lab. So this is a weaker solution. It's about 10 times weaker. That means they took 1 part of the concentrated solutions and add 9 parts of water to it, so it decreased our concentration. So this is a conversion factor we can now use. What does this conversion factor allow us to convert between? I want someone to put it in a sentence. Kevin?
From the quantity of moles to the amount of solution.
To the amount of solution and what?
Volume.
Volume. Great. So if we know the volume of solution that we have, we can determine how many moles are contained within that. Or if we know how many moles we want, we can find out how much volume we need. This is a conversion factor. I do not want to see anyone writing this first because it is not a quantity. It is a way to convert from liters to moles, moles to liters of HCl. So then we're going to go ahead and write out what I heard some people say. Our starting quantity is 0.570 moles of HCl. Write that over 1 because it's our starting quantity. It only has 1 unit. And then how do we use molarity? Do we use it the way it is or do we flip it to use that conversion factor?
Flip it.
Let's try flipping it. To get 1.25 moles of HCl, we need 1 liter of HCl solution. So if we don't plug this in our calculator yet, do you expect our answer to be greater or less than 1 liter of solution? Why less? If we take 1 liter of solution, we're going to get 1.25 moles. So is our quantity greater or less than 1.25 moles? That's what I want you asking yourself. Whenever you see this, or the molar mass for that matter, if I want 13 grams of carbon, I should know before I do any calculations that's going to be greater than 1 mole of carbon, because carbon is 12 grams for 1 mole. Okay? So if we do our calculations, our conversion here, from the number of them in moles to how much volume we need, what do we find? Angel, what was your calculation here?
Oh, I didn't actually get it.
Okay, Kayla?
I have 456.
456. So if I stop right here, why would I not get 456? So I didn't convert it to milliliters. So you can either do that afterwards, but I would ideally do it all in one. So let's do that. What's the last conversion factor I need then to convert from liters to milliliters? 1 liter is 1,000 milliliters. And I'm going to focus in on one thing here too. So we converted from moles of HCl to liters of HCl solution. But then for the second conversion, I actually honed in just on the liter component. Notice how we didn't cancel out HCl solution, but we converted from liters to milliliters. So I saved the HCl solution, and now it's just the milliliters in front of it. If you're very careful with your unit conversions, you can do that, and you can just cancel out part of your units. If you have a kila somewhere, you can say, well, kila is 1,000 of whatever that thing is. So you said 456 units?
Milliliters of HCl.
Great. So what this statement says is that in order to get 0.570 moles of HCl from this solution, I would need to take out 456 milliliters of that solution. We can either describe it as the volume or the number of moles, but those are identical because we know it came from this solution. That ratio should still be the same. How do we triple check that ratio to make sure that ratio is legit? Could we check it? How?
You just divide 0.57 moles of HCl divided by that 456.
So if we divide the number of moles by the number of liters, as long as we do liters and not milliliters, right? So this is 0.456 liters. We should get 1.25. That ratio will always stay the same. All right, let's go ahead and try another one. This would be a great exam question. Also a great lab question. You guys can do this.
You don't have a mole per, you have how many moles. So
Wish I wasn't like the
problem a little trickier? We're just taking two things you've done and we're putting them together. So I saw a number of people, we start calculating how many moles of potassium carbonate we have. In order to do that, we need a formula, right? What's the formula for potassium carbonate?
K2CO3.
Carbonate has a -2 charge, that polyatomic ion, so we need 2 potassium 1 pluses to make a neutral salt. But if I figure out the moles of it, I'm stuck. Then what do? If I know how many moles of potassium carbonate, how do I do anything about how many moles of HCl? So what is the next step we do, Kayla? But then what? So somehow we have to get from moles of potassium carbonate to moles of HCl. Christina, how do we do that?
Wouldn't you have to make the formula first and like do the ratio of potassium carbonate to hydrochloric acid?
So we're talking about a chemical reaction here. We're talking about that a base, potassium carbonate, will react with an acid, HCl. So we're going to go ahead and write out the formula for that. And honestly, I don't care about the right side of this equation because we're only asking reactants to reactants. So what ratio do we need of K2CO3 to HCl?
2.
2 of which?
2 HCl.
I guess we do need to write the right side of the reaction, right? Okay, what products are you making?
Potassium chloride and hydrocarbonate.
H2CO3. All right. Sorry about that. Totally true. Mohit?
When you make H2O and CO2, like in the lab?
So when you do an acid-base reaction, you do generate from H2CO3 in solution, breaks down into water and CO2. So that's what you will see in lab, is that you actually have a secondary reaction that generates H2O plus CO2. But for now, for this problem, it's fine to do either one of those two as your products. Once you do it in lab, you will see bubbles coming off. And those bubbles are from H2CO3 breaking down into water and CO2. So technically it's 2 steps, but in lab you'll see it as 1. So then if we're doing that, how we have a balanced equation then? Almost. What else do we need to do? We generate 2 potassium chlorides. So then let's go back and write out, we're going to use that now to answer this question. So we know that we have 4.367 grams of K2CO3. How do we find the number of moles? 1 mole of K2CO3 weighs how many grams? You guys look this up? Say again?
138.
Okay, and then now we know how many moles of potassium carbonate we started with. Trey, what do we do next?
You would do the ratio between moles of potassium carbonate and hydrochloric.
Great. So we know that to consume 1 mole of potassium carbonate, we need to use 2 moles of HCl. Then what? Do we do what we normally do and use the molar mass to find the grams of HCl here? That's an extra step we don't need to do because then we need to convert back from grams to moles, so that's a waste of time. So what's our next conversion to answer this question, Bria? Gail?
Well, I think you do what you did last problem. You take those moles and then you convert the moles to moles, liters, and then from liters to milliliters.
Great. So we can use the molarity. If we unpack this big M right here, we know that's 2.75 moles of HCl are in every 1 liter. So now if we have the number of moles of HCl, we can find the liters of solution that contain that many moles. So 2.75 moles of HCl are contained in every 1 liter of this particular HCl solution, as I'm running out of space. And then as Gail said, if the answer asks for it in milliliters, we know that 1 liter is the same as 1,000 milliliters. What did you get for your answer then?
92.94 milliliters.
Great. If we don't put solution, we're referring to just HCl, so I want to try to be as specific as we can and say it's that many milliliters of HCl solution. Do we have the right number of sig figs here?
No.
Why? Where do we limit our sig figs? There's 4 sig figs right here. He's right.
There's 3 in the HCl.
But the concentration of the HCl was not known to as much accuracy, so we only have 3 sig figs. These are the only 2 numbers we use to base our sig figs because those are the only 2 numbers that were measured by someone and given to you, as opposed to this is an exact ratio, and this is a number we can look up a much more accurate version than what's on the periodic table, so we're not going to use that to limit our sig figs. So that means that our final answer would be not moles, right? Joey?
I got 0.98.
Yeah, so mine would round up to 23.0.
So it'd be 23.0 if I got 98, right?
Okay, so I didn't do the calculations in front of me, so
I'm just asking if I got 98, it would be 23.0, right?
yes,
Okay.
you would round up if you got 0.98, correct. So I would go back and make sure to check your calculations. If you're using your iPhone for calculations, it might be more difficult. I would always suggest using the calculator you will use on the exam. You cannot use your own graphing calculator in exam 3. You can use one of my, you can loan one of my calculators with an ID for exam 3. For the ACS final exam, you will not be allowed to use any graphing calculator. So I would advise if you have one of these inexpensive scientific calculators, learn how to use it, and then use it on the exams if you're comfortable with it. If not, on all the exams that I write, you will get a chance to use it. All right, any questions? You guys comfortable seeing how we can use this conversion factor now? I want you to be able to answer questions forwards and backwards. There's some more questions on the homework about that. Caleb?
Already answered it.
Great, yes, there will be practice questions on the homework. One thing going, one step further. If we were to say how, no, we'll get into that next week. All right. So there's another problem listed on here you can do as a practice problem I gave you. You also have homework questions that you can do. So, our learning objectives for today. Determine the number of moles in a given solution. If we know the molarity, kind of go forwards and backwards, how much we would need. And now we're going to start talking about percent mass. Empirical formula, molecular formula, and determining the identity of an unknown. So let's dive right into that. So if we jump into our first question, if we think about a water molecule, which of these best describes where the mass of that water molecule comes from? A couple more seconds. All right, we have an overwhelming majority for oxygen. Why? Can I get someone to describe why we would say that the majority of the mass of a water molecule comes from oxygen? Can I hear from Eric?
Because oxygen is vastly heavier than both hydrogen.
Why? Why is oxygen vastly heavier than the hydrogens? Manu?
It has more protons and
Fantastic. So when we're talking about this, I don't want you to forget everything we've done so far and just say, oh, oxygen's heavier, right? I want you thinking about each oxygen atom, on average, has 8 protons and 8 neutrons, which means it has a lot more mass than a hydrogen that typically has 1 proton and no neutrons. All right, so then we're going to take that mentality, and we're going to go ahead and calculate the percent of the mass of water that comes from each of the elements. Let's do oxygen first. I'm just looking at the clock, and I'm thinking I might want to do a more challenging problem. Is this... Let me walk you through this one. I hate doing that, but just for the sake of time, I want to have you get a little bit of time in the more challenging questions. Big picture, how are we doing this? Great. Mass of the oxygen over the total mass. So we have the total mass of water is 18 AMU, or grams, if we're talking about a mole. And then the mass of oxygen is 16 out of those 18. So we can figure out precisely how much of that mass comes from oxygen. And then the rest of that, the other 11.2%, that comes from the rest of the molecule. In this case, there's only hydrogen. So we can figure out the relative amount of the mass that comes from each of those two. Let's do... Let's do a harder question. Let's do... Are you guys comfortable with the terms? Have you seen empirical molecular formula? I think that was in your homework? Possibly? So let's look at the difference between empirical and molecular formula. For water, it's the same. What would the empirical formula be for this sugar? Matthew, what would it be in what?
CH2O.
Why?
Because you can divide the amount of atoms of each element. They're all divisible by 6.
Great. So you can simplify the ratio down. So there's 1 carbon for every 2 hydrogens for every 1 oxygen. Does that mean that glucose actually is this? No, it's a ring of 6 carbons that has 12 hydrogens and 6 oxygens attached to it. This one describes what the molecule looks like and the actual mass. This one only describes the ratio of the elements in that molecule. What about hydrogen, rocket fuel? Straight up NH2. All right? So what we're going to do now is we're going to think about combustion analysis that I mentioned last class will allow us to find the ratio between carbons, hydrogens, and oxygens. Is that going to allow us to find the empirical formula or the molecular formula? It's only going to be the empirical. And unless we have the mass spec data to tell us how heavy it is, we can't go backwards and figure out the molecular formula. Ionic compounds, which ones do they use? Do they use the molecular formula or ionic formula? Do you ever see Na23Cl23?
No.
What about K4 carbonate 2? All right, so for ionic compounds, we're always going to use the empirical formula. It's called the formal unit when you're talking about ionic compounds, but name doesn't matter. We use the whole lowest whole number ratio. So let's go ahead and do this guy. Raise your hand if you get stuck. Those of you who might not be so comfortable starting, does that percentage change if we have 10 grams versus 15 grams versus 20 grams? So let's just start with, just pick a mass, pick a certain amount. I usually pick something base 10. So say we're working with 10 grams. How many grams of carbon do we have if we have 10 grams total of the compound? How many grams of hydrogen do we have? Does that help? Once you know the number of grams, what can you figure out? You can figure out how many moles we have of each. So go ahead and pick a quantity. Figure out how many moles we have of each of the two, and then look at the relative amounts of both. All right, so let's work through this, because this is a little bit of a challenging problem. So I picked 100 grams as my amount that I had of this unknown compound. If I have 100 grams of it, then I know that 82.67 grams of that 100 grams come from carbon, and 17.33 grams of that 100 grams are coming from hydrogen. If you know the number of grams, how do we find, so we're talking about the mass, right? How do we find how many of them there are? Motive?
Do you divide it by the grams of the least weighing thing, in this case would be hydrogen?
So if we're trying to find the ratio of carbon to hydrogen, can we compare the mass of them directly? We have to talk about how many of them there are, so we cannot divide the masses by each other. Let's convert it to moles. So let's find how many moles of each of these we have. Can you guys do that?
Yep.
So if we do that for 100 grams, I find that we have 6.88 moles of carbon for every 17.19 moles of hydrogen. It's really important that you don't say, in this compound we have 6.88 moles of carbon. It's only when we have 100 grams that we have this many moles of carbon, and the most important thing is the ratio between these two. So Moab, what can we do now? Now that we know how many of each we have, divide what by what?
By the mass of hydrogen.
By the what?
The moles of hydrogen.
Okay, so we want to say, what is the ratio of these? Just eyeballing it, what does it look like? It's about 1 to 2 maybe, ish. So I don't know, my math's not that great in my head, so I'm going to go ahead and do the calculations. I'm going to find that ratio, and we're always going to divide by the smallest number. Otherwise we're going to end up with a lot of fractions, and that's useless to us. So we're going to divide by the smallest number, because then our smallest number is always going to be 1. So we know that for every 1 carbon, we have 2.5 hydrogens. Great, I found my empirical formula, right? CH2.5.
Wrong. Because you can't have 0.5.
We can't have 0.5 hydrogen atoms. So then what's our empirical formula? We know the ratio is 1 to 2.5. So then we can multiply that by a factor of 2. And then we can find the lowest whole number ratio between those guys. So then the last question that I would ask, if we know the molar mass, is that empirical formula the molecular formula? What is the weight of 2 carbons and 5 hydrogens? It's like 29 grams per mole. We know that the molecule itself weighs 58.
So it must be C4H10 because that looks to be double.
Alright, I've kept you guys way long. I do have my exam review today from 1 to 2:30 in E-Task 125, which is literally the bottom of the building right next to us. In this closest corner, there's a big open office space that we'll be using, not the classroom in that suite.
You guys been watching?
Thank you, dude.
No.
So divide the math.
You're saying then that all of the